Have you ever looked up at the night sky and wondered what lies beyond the stars we can see? We often think of the universe as this vast, endless expanse. But what if I told you that everything out there, every galaxy, every cluster, every speck of light, might be moving towards something we can't even see? Something so powerful, so mysterious, that it's pulling entire galaxy clusters toward it like a cosmic river flowing toward an unseen ocean. This isn't science fiction. This is one of the most baffling discoveries in modern cosmology, a phenomenon scientists call dark flow. Imagine for a moment that you're watching leaves drift down a stream. They all move together, swept along by currents too powerful to resist. Now picture that on a scale almost impossible to comprehend, not leaves but galaxies, each containing billions of stars, all drifting in the same direction, pulled by a force originating from beyond the edge of everything we can observe. This is the mystery of dark flow, a discovery that challenges our very understanding of the universe. It suggests that there might be structures or influences far beyond what we once thought was the cosmic horizon, something immense and unknown tugging at the fabric of space-time itself. This journey we're about to take together isn't just about facts and figures. It's about diving into one of the greatest enigmas of our time. A mystery that invites us to question what we know, to wonder about what lies in the unseen reaches of existence, and to feel that thrill of curiosity that has always driven humanity to look up and explore. Over the next while, we'll uncover 30 astonishing facts about dark flow, each one peeling back another layer of this cosmic puzzle, each one bringing us closer to the edge of known reality. So settle in, open your mind, and let's embark on this adventure into the unknown, where the answers we find might just reshape everything we thought we knew about the universe. Our story begins not with a dramatic announcement, but with a meticulous analysis of the faintest glow in the universe. For years, scientists had been studying the cosmic microwave background, the afterglow of the Big Bang that permeates all of space. This ancient light is like a baby picture of the cosmos, and by examining its tiny temperature variations, researchers can understand how matter was distributed in the early universe. The Wilkinson Microwave Anisotropy Probe, or WMAP, was a NASA satellite designed to create the most detailed map of this radiation ever seen. Its data was expected to confirm and refine our existing models of cosmology. But as a team led by astrophysicist Alexander Kashlinsky pored over the results in 2008, they found something that simply didn't fit. They were using a clever technique to detect motion on a colossal scale. It's similar to the Doppler effect you experience when a police siren changes pitch as it races past you. The team was looking for a subtle shift in the cosmic microwave background caused by the movement of enormous galaxy clusters. They expected to see a random, chaotic pattern of motions, with clusters drifting in all directions as the universe expands. Standard cosmology predicted that on the largest scales, the universe is homogeneous and isotropic, meaning it should look roughly the same in every direction with no preferred flow. What they found was profoundly different. Instead of random motion, the data revealed a startlingly coherent flow. Hundreds of galaxy clusters, each containing the mass of 1,000 Milky Ways, were all moving in the same direction at astonishing speeds of nearly 2 million miles per hour. This wasn't a local phenomenon, it was a bulk motion on a scale that defied explanation. The gravitational pull of all the known matter in the observable universe shouldn't be strong enough to cause such a synchronized and powerful drift. It was as if these clusters were caught in a cosmic current, being pulled by something immense that lay far beyond the edge of everything we can see. This was the moment the term dark flow was born, not just as a name, but as a label for a profound mystery that challenged the very foundations of modern astrophysics. This coordinated drift is happening on a scale that is genuinely difficult to grasp. We're not talking about a few nearby galaxies swaying gently under the influence of their neighbors. The motion detected involves thousands of massive galaxy clusters, all moving in concert across unimaginable voids. Their speed is a constant 1,000 kilometers per second, a velocity so immense that it would allow you to travel from Earth to the Moon in a mere 6 minutes. And this isn't a short, localized dash. It's a relentless journey that has been ongoing for billions of years, carrying these colossal structures across billions of light-years of space. To put that distance into perspective, a single light-year is about 9.5 trillion kilometers. The scale of this motion involves distances so vast that the light we see from these clusters today began its journey to us before our planet even formed. What makes this even more extraordinary is the sheer size of the structures being moved. A single galaxy cluster is one of the most massive gravitationally bound objects in the universe, often containing thousands of individual galaxies, enormous clouds of hot gas, and incomprehensible amounts of dark matter. They are the metropolises of the cosmos, the idea that not just one, but thousands of these behemoths are being pulled in the same direction suggests the source of this pull must be something of almost inconceivable mass and power. The gravitational force required to orchestrate this motion on such a scale far exceeds the combined pull of every known galaxy, star, and filament of dark matter within our entire observable universe. It implies an influence originating from far beyond our cosmic horizon, from a region of space whose light has not had enough time since the Big Bang to reach us. We are, in effect, sensing the gravitational shadow of something that lies forever outside our field of view, a reminder that our observable universe might just be a small part of a much larger and more mysterious structure. So what exactly is it that's caught in this immense cosmic current? We're not witnessing the drift of individual stars or even solitary galaxies. The scale here is almost beyond human comprehension. This flow involves the largest known structures in the universe, galaxy clusters, and the even grander formations they comprise, known as superclusters. A single galaxy cluster is a sprawling metropolis of hundreds or even thousands of individual galaxies, all bound together by gravity, swimming in a vast sea of superheated gas and enveloped by a massive halo of dark matter. These clusters themselves can group together, forming superclusters that stretch across hundreds of millions of light-years. It is these titanic assemblies, these archipelagos of galaxies, that are moving in unison. Picture the largest river system on Earth, like the Amazon, with countless tributaries all feeding into one powerful, central flow. Now magnify that image to a cosmic scale. Each tributary is a filament of galaxies, each droplet of water is an entire cluster, and the river itself is a coherent stream of matter on a scale so vast it challenges the limits of our instruments. This isn't a gentle drift, it's a structured, coordinated motion. Thousands of these massive clusters, each one a gravitational anchor in its own right, are all participating in this grand directional march. They are not simply being carried by the expansion of the universe, which pushes galaxies apart, but are instead being tugged sideways by a force that transcends that expansion. This creates a breathtaking image of the cosmos not as a static expanse, but as a dynamic, flowing entity. We are witnessing a cosmic river of matter, where the very largest building blocks of our universe are all streaming toward a common, unseen destination. The coherence of this motion is what makes it so mysterious. For these clusters to move together, they must be responding to a gravitational gradient, a slope in the fabric of space-time, that is both incredibly powerful and astonishingly uniform across billions of light-years. It suggests an underlying architecture to the cosmos that we are only just beginning to sense, a structure so immense that it makes our entire observable universe seem like a local neighborhood. This discovery of a coordinated flow on such an immense scale sends a tremor through one of the most fundamental pillars of modern cosmology, the cosmological principle. This principle is not just a minor guideline, It's the very foundation upon which we've built our entire understanding of the universe's structure and evolution. It states that, on sufficiently large scales, the universe is both homogeneous and isotropic. Homogeneous means the matter in the cosmos is smoothly distributed, like a well-mixed batter. No single region is significantly denser or more special than any other when you zoom out far enough. Isotropic means it looks the same in every direction you look. There is no preferred center or edge, no cosmic north or south. For decades, our observations seem to support this idea beautifully. The cosmic microwave background radiation, that fossilized light from the early universe, shows only incredibly tiny temperature variations, telling us the infant cosmos was remarkably smooth. The large-scale distribution of galaxies, when mapped, appears as a vast, frothy web of filaments and voids, but statistically, it seems to even out across billions of light-years. Our entire standard model of the universe, including the theories of dark energy and dark matter, rests upon this assumption of a uniform cosmos. It's the reason we can confidently talk about the universe as a whole and apply the same physical laws everywhere. Dark flow directly and profoundly challenges this core assumption. A coherent, directional motion of galaxy clusters on a scale of billions of light-years is the very definition of something that is not isotropic. It introduces a preferred direction into the cosmos, a specific axis along which this immense river of matter is flowing. If the universe were truly the same in all directions, such a massive, synchronized drift should not exist. The gravitational pulls from all the known matter we can see should cancel each other out on these enormous scales, resulting in random, chaotic motions, not a unified march toward a single point on the horizon. This suggests a staggering possibility that the observable universe, the portion we can see and study, may not be a fair sample of the whole. There could be structures or density variations on scales so vast they lie beyond our cosmic horizon, regions whose light has not had time to reach us in the nearly 14 billion years since the Big Bang. Imagine living in a valley and believing the entire world is as flat as your surroundings, unaware of a massive mountain range just over the horizon whose gravitational influence is still felt in your local streams. Dark flow hints that we might be in a similar cosmic valley, and the pull we're detecting is the gravitational shadow of a mountain range of matter so colossal it defies our current imagination. This isn't just a new mystery to solve, it's a potential paradigm shift, forcing us to reconsider whether the laws and principles we believe to be universal truly apply to the entirety of existence. This idea of a hidden, overwhelming gravitational influence might sound familiar to some of you because cosmology has faced a puzzle like this before. In the 1970s and 80s, astronomers mapping the motions of nearby galaxies made a curious discovery. Our entire local group, including the Milky Way and Andromeda galaxies, isn't just moving with the expansion of the universe. It's also being pulled in a specific direction toward the constellations of Centaurus and Hydra. The source of this pull was dubbed the Great Attractor, a mysterious region of space with the mass of tens of thousands of Milky Way galaxies, which acts like a gravitational anchor for all the galaxies in our intergalactic neighborhood. For a long time, the Great Attractor remained shrouded in mystery because it lies directly behind the plane of our own galaxy, a zone obscured by thick clouds of gas and dust that our telescopes couldn't peer through. It was like trying to see a distant city through a dense, permanent fog. With the help of infrared and X-ray observatories that can see through this cosmic veil, we eventually identified the core of this anomaly as a massive concentration of galaxy clusters, a gravitational heart powerful enough to steer the motion of our entire local supercluster. It was a monumental discovery that showed us the universe is full of these large-scale flows. But here's the crucial distinction, and it's a breathtaking one. The Great Attractor, for all its immense power, is a local phenomenon. It influences matter on a scale of a few 100 million light-years. Dark flow is something else entirely. It operates on a scale that is orders of magnitude larger. The clusters caught in the dark flow are not just being pulled by a single, albeit massive, knot of matter within our observable universe. Their motion suggests an influence that originates from beyond the observable universe. If the Great Attractor is a powerful regional current pulling galaxies into a bay, then dark flow is the entire ocean itself being tugged by the gravitational pull of another continent so far away we can't even see its shore. This comparison highlights the profound shift in thinking that dark flow demands. The Great Attractor, once the biggest mystery in the room, is now understood to be just one part of the cosmic structure within our visible horizon. It is a puzzle we are slowly solving. Dark flow, however, points to a reality where the structure doesn't end at our horizon. It implies that the Great Attractor itself and our entire observable universe might be just a single leaf caught in a much vaster, more powerful cosmic river, all flowing towards something unimaginably large waiting in the darkness beyond. Detecting a motion as subtle yet immense as dark flow required a tool of extraordinary precision, and physicists found it in a faint but telling signature within the oldest light we can see. The method hinges on a phenomenon called the kinetic Sunyaev-Zel'dovich effect, named after the two Soviet scientists who first predicted it. To understand how it works, picture the cosmic microwave background as a uniform, ancient wall of light that fills every corner of the universe. Now imagine a massive galaxy cluster moving through space. This cluster is filled with incredibly hot electrons, part of the superheated gas that resides between its galaxies. As the photons from the cosmic microwave background journey across the cosmos, they inevitably pass through these galaxy clusters. When a CMB photon collides with a fast-moving electron in that hot gas, something fascinating happens. The photon gets a tiny boost of energy. It's similar to how a tennis ball would fly off with more speed if it were hit by a swinging racket rather than a stationary one. This energy transfer imparts a minuscule but measurable change to the photon's temperature. If the electron cloud is moving toward us, the photons get a bit warmer. If it's moving away, they appear a fraction cooler. The true power of this technique lies in its ability to isolate this specific signal from the rest of the cosmic microwave background's variations. Researchers aren't just looking at one cluster, they compile data from thousands, meticulously mapping these tiny temperature shifts. By analyzing the collective pattern of these distortions, they can deduce not just if a cluster is moving, but the exact direction and velocity of its motion across the sky. It's an astronomical feat of detective work, allowing scientists to measure movements of incomprehensible scale by observing the faintest whisper of a temperature change in the afterglow of creation. This method provided the first clear, irrefutable evidence that thousands of these colossal structures were not drifting randomly, but were all swept up in the same coherent, mysterious flow. Of course, a discovery this profound and paradigm-shifting was never going to be accepted without a fierce and healthy debate. In the world of science, extraordinary claims require extraordinary evidence, and dark flow is about as extraordinary as it gets. The initial findings sent a ripple of excitement through the cosmology community, but it was quickly followed by a wave of intense scrutiny and skepticism. This isn't a sign of failure, it's how science self-corrects and strengthens itself. The controversy surrounding dark flow is a fascinating story in itself, a clash of ideas at the very frontier of our understanding. A primary line of skepticism focuses on the data itself and the potential for hidden errors. Could this seemingly coordinated motion be a mirage created by our own instruments or our methods of analysis? Some researchers have argued that the detected signal might be contaminated by other astrophysical foregrounds, emissions from within our own galaxy, or from other distant sources that weren't perfectly filtered out. Imagine trying to hear a single, quiet instrument in a vast orchestra. If your microphone isn't perfectly tuned, you might mistake the sound of a clarinet for a flute. Critics have proposed that subtle systematic errors in the calibration of the satellites or in the complex statistical algorithms used to isolate the kinetic Sunyaev-Zel'dovich effect could be creating this apparent flow where none exists. They contend that the signal is at the very limits of what these telescopes can detect, living in the noisy outskirts of the data where it's easiest for artifacts to be mistaken for reality. This statistical uncertainty is another major battleground. Other teams using different catalogs of galaxy clusters or alternative methods to analyze the same raw data from the WMAP and later the Planck satellite have reported that the signal either vanishes or becomes significantly weaker. They suggest that the original team might have inadvertently cherry-picked clusters or used a processing technique that amplified a random statistical fluctuation into something that looked meaningful. In a universe as vast and complex as ours, random alignments can and do happen. The question is whether dark flow is a real physical phenomenon or the cosmic equivalent of seeing a face in the clouds, a pattern our brains impose on randomness. These researchers aren't accusing anyone of misconduct. They are simply upholding the rigorous standard that a result isn't robust until it can be consistently reproduced by independent methods. Then there are the theorists who accept that the motion is real but seek explanations that keep us within the comfortable confines of the known universe without invoking mysterious beyond-the-horizon influences. Could an immense, previously undetected supercluster, a structure of almost mythical proportions, exist within our observable universe and be responsible for this pull? While the scale of dark flow makes this seem unlikely, as it would require far more mass than we believe exists in our visible cosmos, it's not entirely impossible if our inventories of ordinary and dark matter are profoundly incomplete. Other more exotic proposals involve tweaking our understanding of gravity itself on the largest scales, perhaps through modifications to Einstein's theory of general relativity. If the laws of gravity work differently over billions of light years than they do in our solar system, it could create unexpected large-scale flows without needing any unseen mass. This vibrant, sometimes heated, debate is the engine of scientific progress. The team that discovered dark flow, led by Alexander Kashlinsky, has consistently defended their methodology, addressing criticisms with refined analyses and pointing to consistent signals across different datasets. They argue that the coherence of the flow across thousands of clusters is simply too striking to dismiss as an error. This back and forth is a perfectly normal, if slow and meticulous, process. It pushes both sides to sharpen their arguments, improve their techniques, and seek ever more precise data. The true nature of dark flow won't be settled by one decisive paper, but through years of collective effort, observation, and replication. This controversy isn't a weakness of the finding, it's a testament to its immense potential importance. Scientists are arguing so passionately because the stakes couldn't be higher. The outcome could either neatly fold into our existing cosmic model or force us to tear out the page and start a whole new chapter. This coordinated motion isn't random or chaotic. It possesses a specific, well-defined direction, almost like a cosmic compass pointing toward a single, mysterious destination. The data from multiple studies consistently shows this immense river of galaxy clusters all streaming toward a particular patch of our sky, located in the general direction of the southern constellations Centaurus and Hydra. This isn't a vague area, it's a precise alignment, an axis along which this incomprehensible force is acting. When we talk about distances in the universe, we often deal in approximations, but the estimated location of whatever is doing the pulling is thought to lie at a staggering distance of between 10 and 20 billion light-years away from us. Now, that distance is itself a crucial part of this profound mystery. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46.5 billion light-years. This means the suspected source of dark flow lies far beyond the reach of our most powerful telescopes. Its light simply hasn't had enough time in the entire history of the cosmos to travel to us. We are, in effect, sensing the gravitational shadow of something that is fundamentally unseeable, a presence we can only infer from its immense pull on everything within our visible horizon. It's like trying to deduce the existence of a massive mountain range on a distant continent solely by observing the consistent flow of rivers in your own country, all running toward a coast you cannot see. This precise directional alignment is perhaps the most compelling evidence that we are dealing with something truly monumental. For thousands of galaxy clusters scattered across billions of light-years to all share a common velocity vector points to a gravitational gradient that is both incredibly powerful and astonishingly uniform. It suggests the source isn't just a single, colossal object like a supercluster, which would create a more focused, cone-like pattern of attraction. Instead, this coordinated pull hints at something even more immense, a vast, extended structure or a profound asymmetry in the density of the cosmos on scales we once thought were smooth and featureless. We might be living in a corner of a much grander universe, one where our entire observable cosmos is just a small part of a larger structure, and this dark flow is the gentle but undeniable slope down which we are all sliding. To truly grasp why dark flow is so disconcerting to physicists, we need to place it alongside the other great, dark mysteries of cosmology, dark matter and dark energy. While their names sound similar, each represents a fundamentally different kind of puzzle, and understanding their distinctions is key to appreciating the unique enigma of dark flow. Let's start with dark matter, the most established of the three. We've known something was amiss since the 1930s, when astronomers like Fritz Zwicky noticed that galaxies within clusters were moving far too quickly to be held together by the gravity of the visible stars alone. It was as if the entire galaxy was a tiny, glowing light on the tip of a massive, invisible iceberg. We cannot see dark matter because it does not emit, absorb, or reflect light. It interacts with the universe almost exclusively through gravity. Its primary role is that of a cosmic architect. The gravitational pull of dark matter provides the scaffolding upon which galaxies and galaxy clusters form. Without its immense, unseen mass, the universe as we know it would simply fly apart. We can map its distribution, measure its effects, and while we still don't know what it's made of, we understand its job. It provides the extra gravity that holds the cosmic structures together. Then there's dark energy, a concept that emerged much later in the late 1990s. While dark matter is a pulling force, dark energy is a pushing force, and a bizarre one at that. Observations of distant supernova revealed that the expansion of the universe is not slowing down, as everyone expected due to gravity, but is actually accelerating. Something is actively working against gravity, stretching the very fabric of spacetime itself at an ever-increasing rate. This something is dark energy. It's not a material substance like dark matter. It's often described as a property of space. Its effect is smooth, uniform, and repulsive, acting everywhere at once to drive galaxies apart from each other. Its role is to govern the expansion and ultimate fate of the entire cosmos. Now enter dark flow. Unlike its two famous counterparts, dark flow isn't about the amount of matter in the universe or the rate of its expansion. It's about motion. Specifically, it's a mysterious, directional motion superimposed on the other two processes. Imagine a vast, calm ocean representing the expansion driven by dark energy. On that ocean, there are fleets of ships, our galaxy clusters, that are not only drifting apart with the expanding water, but are also all being pulled in the same direction by a powerful, unseen current. That current is dark flow. Dark matter builds the structures and dark energy dictates how the space between those structures grows. But dark flow suggests that these entire structures are also on the move in a coordinated way that shouldn't exist according to our standard model. It's not explained by the gravitational pull of any known dark matter structure, and it's certainly not caused by dark energy, which drives a uniform expansion, not a directional tug. This makes dark flow a separate, independent mystery, a third, dark phenomenon that doesn't fit neatly into our existing cosmic box. It hints that there might be a whole other layer of influence on the universe, one that operates on such immense scales that it connects our observable cosmos to the utterly unknown realms beyond. This concept of an influence from beyond our sightline connects dark flow to one of cosmology's most enduring puzzles, the horizon problem. At its heart, this problem questions how the universe achieved such a uniform temperature. The cosmic microwave background radiation, that ancient afterglow from the Big Bang, is almost perfectly even across the entire sky. The temperature varies by less than 100,000th of a degree from one region to another. This presents a profound conundrum because, according to the standard model of the universe, these distant regions should never have been in contact with each other. To understand why, we need to consider the speed of light and the age of the universe. In the very early cosmos, 2 points on opposite sides of the sky today were separated by a distance so vast that light, traveling at the universe's speed limit, would not have had enough time to move between them and allow them to reach a common temperature. It's like walking into a massive, crowded party and finding that every single guest, even those who arrived from completely different cities without communicating, is wearing the exact same outfit down to the smallest detail. How could this incredible coordination have possibly happened? The leading solution for this is a theory called cosmic inflation, which proposes that the infant universe underwent a period of exponentially faster than light expansion, smoothing everything out before the laws of physics as we know them took hold. Dark flow adds a fascinating and mysterious new layer to this classic problem. Inflation would have created a smooth and uniform universe, but it should have also erased any pre-existing directional preferences like the one we see in the dark flow. The fact that we observe this coherent motion suggests that the conditions which set up this flow must have existed either before the inflationary period began or were imposed on our entire observable universe from the outside. It hints that the initial conditions of our cosmic patch were not perfectly isotropic. There was a tiny, fundamental asymmetry written into the fabric of our region of space-time, a kind of cosmic slope that inflation did not completely erase. This primordial tilt, this preferred direction, could be the very thing that is still driving the motion of galaxy clusters billions of years later. In this way, dark flow isn't just a modern anomaly. It might be a living fossil, a remnant of the universe's very first moments, offering us a rare and precious clue about what happened at a time and from places we can never directly observe. The quest to resolve the intense debate surrounding dark flow required a new level of precision, a tool even more sensitive than the WMAP satellite that first spotted the anomaly. That tool arrived in the form of the European Space Agency's Planck satellite, a marvel of modern cosmology launched in 2009. Planck was designed to map the cosmic microwave background with unprecedented resolution and sensitivity, and its data was eagerly anticipated by both supporters and skeptics of dark flow, each hoping it would definitively prove their case. What the Planck data ultimately delivered, however, was not a simple verdict but a far more nuanced and complex picture that continues to fuel scientific discussion to this day. For the team that discovered dark flow, the initial results from Planck were a significant vindication. When researchers applied the same kinetic Sunyaev-Zel'dovich analysis to Planck's richer, cleaner dataset, they again found evidence of a large-scale bulk flow. The signal was there, confirming that the original detection was not merely an artifact of WMAP instrumentation. This independent confirmation from a more advanced satellite was a powerful rebuttal to critics who had dismissed the finding as a data processing glitch. It strengthened the case that this mysterious motion was a real physical phenomenon happening out in the cosmos, not just a ghost in the machine of our telescopes. However, the Planck data also introduced new challenges that complicated the original dark flow hypothesis. While it confirmed the existence of a bulk flow, the measured amplitude, the sheer speed and power of that flow, was lower in the Planck data than what had been reported from the WMAP observations. According to Planck's measurements, the clusters were moving at a slower velocity, and the coherence of the flow might not extend to quite as grand a scale as originally claimed. This didn't make the flow vanish, but it did pull it back from the most extreme interpretations. It was no longer a current rushing at 2 million miles per hour. It was still a powerful drift, but perhaps a slightly less overwhelming one. Furthermore, the Planck collaboration's own official analysis painted a more conservative picture. Their preferred methods for filtering out foreground interference from our own galaxy led them to conclude that the evidence for a flow on the very largest scales was inconclusive. They suggested that the remaining signal could potentially be explained by the gravitational pull of known, albeit immense, structures within our observable universe, like the Shapley supercluster, which is the largest known concentration of matter in our local cosmos. This created a fascinating standoff. Two different teams were looking at the same exquisite dataset from the same satellite, but using different analytical techniques and arriving at different conclusions about what it meant. One side saw a confirmed mystery that pointed beyond the known universe. The other saw an intriguing anomaly that might still be explained by known physics, just on a more magnificent scale than we previously appreciated. This ongoing tension is a perfect example of how cutting-edge science often operates not in black and white, but in shades of gray. The Planck satellite didn't kill the dark flow hypothesis, but it did refine it and ground it in a more complex reality. It forced everyone to sharpen their tools and their arguments. The conversation shifted from "is this real?" to "what is its true scale and what is its ultimate cause?" The mystery persists, but it is now a more precise and defined mystery, one that continues to drive the development of new satellites and deeper surveys, all aimed at peering ever further into the cosmic currents that shape our universe. One compelling theory that attempts to explain dark flow without immediately leaping beyond our cosmic horizon involves not what is out there pulling, but what is not there. The universe isn't just made of galaxies and clusters, it's also defined by its emptiness. Vast regions of space, known as cosmic voids, stretch for hundreds of millions of light years, containing very few galaxies and an incredibly low density of matter. According to Einstein's theory of general relativity, gravity isn't just about attraction. It's also about the geometry of space-time, which is shaped by the distribution of both mass and the lack of it. An enormous region of below-average density, a supervoid, could theoretically create a kind of gravitational hill. Matter on the edges of this hill would naturally want to roll downhill toward regions of higher density. In this scenario, the dark flow we observe might not be a pull from an unseen attractor, but a push from a profound nothingness, a gravitational repulsion caused by a neighboring ocean of near emptiness. Imagine you're on a vast flat plain, and just ahead of you is a truly colossal sinkhole, so wide you can't see the other side. The ground isn't just dropping away, the very earth around the hole is subtly tilting downward, urging anything loose to slide toward its edges. Now scale that image up to a cosmic level. If our entire galactic neighborhood were sitting on the rim of one of these unimaginably large voids, the gravitational influence of all the missing mass the void's underdensity could, in theory, create a slope that sets galaxies adrift. This idea elegantly keeps the cause of the flow within our observable universe, relying on known physics rather than speculative realms beyond. However, while elegant in theory, the supervoid explanation faces a tremendous challenge when confronted with the sheer scale and power of the observed dark flow. The gravitational effect of a void is directly proportional to its size and depth, how empty it truly is. To generate a flow powerful enough to move thousands of galaxy clusters at millions of miles per hour, you would need a void of almost absurd proportions. We're talking about an underdense region spanning billions of light years, an emptiness so vast it would dwarf the largest known structures in the universe. The problem is, a void that immense would itself be a glaring violation of the cosmological principle, a feature so massive it would be just as paradigm-shifting as the flow it's trying to explain. Furthermore, such a titanic void would leave a distinct and detectable imprint on the cosmic microwave background, a specific kind of cold spot as light lost energy climbing out of this gigantic gravitational hill. While some large cold spots have been found, none come close to matching the scale and profile needed to account for the coherent motion we see. The supervoid idea is a fascinating and valid avenue of inquiry, but it ultimately seems like trying to explain a hurricane with a gentle breeze. The mechanism is understood, but the required magnitude simply doesn't match our observations, leaving us still searching for a cause powerful enough to move the cosmos. Perhaps the most mind-bending and speculative explanation for dark flow is also the most grandiose. The idea that this cosmic river is not being pulled by something within our universe at all, but by the gravitational tug of another universe entirely. This proposition stems from the multiverse hypothesis, a concept in theoretical physics suggesting our universe might be just one of countless others, each with its own physical laws and properties, existing in a vast, higher dimensional structure often referred to as the multiverse. If these other universes are out there, and if they contain matter, an immense amount of it, then their gravity could, in theory, seep through into our own cosmic domain. The fabric of space-time that separates our universe from another might not be a perfect barrier. Gravitational influence could potentially leak across the divide. Think of it like being in a room and hearing a low, persistent hum from the apartment next door. You can't see the source of the sound, but its vibrations travel through the walls, providing undeniable evidence that something is happening on the other side. In this analogy, dark flow is that cosmic hum. The synchronized motion of our galaxy clusters could be the vibration, the subtle but detectable evidence of a neighboring universe exerting its gravitational pull on ours from a dimension we cannot access or observe. This would mean the flow isn't pointing toward an unseen structure in our universe, but toward the location of an entirely separate universe in the broader multiverse. It transforms the mystery from a question of what is out there to where is out there, suggesting we are not just mapping our cosmos, but sensing the shore of an entirely foreign reality. It is crucial to recognize, however, that while this is a breathtakingly exciting idea, it currently resides firmly in the realm of theoretical speculation. The multiverse itself is not a proven scientific fact, but a consequence of several respected, yet unproven, theories like cosmic inflation and string theory. Proposing that dark flow is evidence for it is a hypothesis built upon another hypothesis. The main scientific criticism is that this idea is, for now, untestable and unfalsifiable through conventional means. We have no way to directly confirm or deny the existence of other universes, let alone measure their gravitational influence. Many physicists caution that invoking the multiverse to explain a perplexing observation can be a conversational dead end, a tantalizing "what if" that doesn't actually advance our understanding because it cannot be investigated with experiments or new data. It risks becoming a modern-day God of the gaps argument, used to explain anything we cannot yet understand with known physics. Yet, despite these valid criticisms, the connection persists in scientific discourse because it represents a potential solution that is, in its own way, elegant. It directly addresses the core problem. The source of the pull must be unimaginably massive and must lie beyond our observable horizon. Another universe fits that description perfectly. It doesn't require inventing new types of matter or energy within our own cosmos. It merely suggests that the totality of existence is far larger and more interconnected than we ever dreamed. So, while the multiverse dark flow link remains a highly speculative frontier, it serves an invaluable purpose. It pushes the boundaries of cosmology into truly profound territory, forcing us to ask the biggest questions possible about the nature of reality itself and our place within a potentially infinite cosmic tapestry. This profound challenge to uniformity strikes at the heart of the inflationary paradigm, the very theory that was developed to explain why the cosmos appears so smooth in the first place. According to the standard model of cosmic inflation, the entire observable universe underwent a period of unimaginably rapid expansion in the first fraction of a second after the Big Bang. This explosive growth, far faster than the speed of light, is supposed to have stretched a tiny, homogeneous patch of spacetime into our vast cosmos, effectively ironing out any primordial wrinkles and leaving behind the nearly perfect uniformity we see in the cosmic microwave background. Inflation predicts a universe that is, on the largest scales, isotropic and homogeneous, a cosmos without a preferred direction or a center. The existence of dark flow, a coherent motion on a scale of billions of light years, is a direct and glaring contradiction to this fundamental prediction. It's as if the universe's most successful smoothing iron left behind a deep, directional crease. This contradiction has forced cosmologists to re-examine and refine the theory of inflation itself. If the data is correct, then the standard version of inflation is incomplete. It didn't erase all the primordial features, it may have locked one in. This has led to the development of more nuanced and complex models of inflation that can accommodate such a vast anomaly. Some theorists propose that what we're seeing is evidence of an initial condition that existed before inflation even began, a tiny, fundamental tilt or asymmetry in the primordial universe that was so potent that not even the fantastic stretching of inflation could completely smooth it out. In this view, dark flow is a cosmic fossil, a relic of a time before inflation started, offering us a rare window into the absolute beginning of everything. The flow's direction would then be a pointer, a kind of cosmic north star indicating the orientation of that initial condition. Other modified inflation models suggest that the process itself might not have been perfectly uniform. The concept of multi-field inflation introduces more than one driving force behind the exponential expansion. Imagine inflation not as a single, smooth engine, but as a complex machine with several interacting parts. The interplay between these different fields could have created subtle, large-scale gradients in the fabric of spacetime, a gentle slope across the entire observable universe. Galaxy clusters would naturally slide down this slope, creating the coherent motion we detect as dark flow. This wouldn't require a pull from beyond the horizon, but would instead be an intrinsic feature of our cosmic landscape, woven into its very structure during its birth. There are even more exotic proposals, such as models where our universe is not a solitary bubble, but one of many that formed and collided within a greater multiverse. In this scenario, the gravitational influence of a neighboring universe bubble, brushing against our own during or immediately after inflation, could have imparted a directional push or pull that became imprinted on the distribution of matter. This would make dark flow not a flaw in inflation, but a predicted signature of a richer, multi-bubble inflationary reality. While these ideas are highly speculative, they demonstrate the creative and profound ways cosmologists are responding to the challenge. Dark flow is no longer just a curious observation. It has become a crucial testing ground for the next generation of cosmological theories, pushing us to determine whether our universe's infancy was as simple and uniform as we once believed, or if its earliest moments were far more complex and textured than we ever imagined. For centuries, astronomers have mapped the cosmos by cataloging ever larger structures. We have galaxies which group into clusters which themselves form immense superclusters hundreds of millions of light years across. These are the giants of our known universe, and according to the cosmological principle, They should represent the upper limit of how matter organizes itself. The gravitational pull required to form anything larger on a scale of billions of light-years simply shouldn't exist within the smooth, expanding fabric of our cosmos. Dark flow shatters this comfortable assumption, forcefully suggesting that the true titans of the cosmos lie forever hidden in the darkness beyond our view, and their gravitational reach is so immense that it can steer the motion of our entire observable universe. This concept redefines our very understanding of what a structure can be. The Laniakea supercluster, which contains our own Milky Way, is a breathtaking example of cosmic architecture spanning over 500 million light-years. It is a vast web of galaxies, all flowing toward a central gravitational point known as the Great Attractor. Yet, for all its grandeur, Laniakea is still considered a local structure, entirely contained within our observable horizon. Dark flow implies the existence of something orders of magnitude larger. We are not talking about a slightly bigger supercluster. We are contemplating formations so vast that our entire Laniakea supercluster would be merely a single neighborhood within it, a suburb of a metropolis whose full expanse we cannot see. The gravitational influence required to cause the dark flow gives us a startling clue to the mass of this unseen structure. To pull thousands of galaxy clusters in a coherent direction, the source must possess a gravitational pull that dwarfs the combined attraction of every known galaxy, every filament of dark matter, and every supercluster within our 46 billion light-year wide observable universe. The simplest explanation is that this source contains far more mass than all of it put together. It hints at a density of matter in that unseen region that is exponentially greater than the average density of our own cosmic neighborhood. We might be living in a relative underdense region, on the outskirts of a continent of matter of such staggering proportions that it warps the space-time around it on a scale we are only beginning to sense. This idea introduces a radical new layer to the cosmic hierarchy. If such immense structures exist beyond our horizon, it means the universe is not smooth and uniform on the largest scales, but is instead lumpy and textured in a way we never anticipated. There could be alternating continents of immense density and corresponding oceans of profound emptiness, a cosmic landscape of features so vast that our entire observable universe is just a single data point within it. Dark flow is our first tantalizing evidence of this grander architecture, the first ripple from a distant shore that tells us our cosmic island is not alone, but is part of a much vaster and more complex archipelago whose full map we may never be able to draw. This leads us to a crucial and fascinating question. Has this mysterious river of galaxies always flowed as it does now, or has its current shifted over the immense span of cosmic time? Investigating the history of dark flow is like a detective trying to determine if a suspect's alibi has changed. It can reveal whether we're dealing with a permanent feature of the cosmos or something more dynamic. To answer this, astronomers have had to become cosmic archaeologists, digging through layers of time by looking at increasingly distant, and therefore older galaxy clusters. The method relies on a fundamental principle of cosmology. Looking out into space is equivalent to looking back in time. The light from a galaxy cluster 5 billion light-years away shows us how that cluster appeared 5 billion years ago. By applying the kinetic Sunyaev-Zel'dovich technique to clusters at different distances, researchers can effectively map the dark flow across different epochs of the universe's history. They can check if clusters that were closer together in the ancient past showed the same coordinated motion as clusters do today. The results from these studies have been nothing short of astonishing, pointing toward a consistency that deepens the mystery rather than solving it. Analyses suggest that the dark flow has not significantly changed its direction or strength for billions of years. The same coherent motion toward the same patch of sky in the constellations of Centaurus and Hydra appears to be present in clusters whose light has been traveling to us for over half the age of the universe. This incredible persistence is a critical piece of the puzzle. It tells us that whatever is causing this flow is not a recent or transient phenomenon. It isn't something that just started tugging on things. It has been exerting this immense gravitational influence for a very, very long time, acting as a steady and constant force throughout cosmic history. This temporal consistency dramatically narrows down the list of possible explanations. A flow that has remained stable over such vast timescales rules out causes that would be inherently unstable or short-lived. For instance, it makes the supervoid hypothesis even more challenging to support. A void is an evolving structure. Over billions of years, gravity would tend to fill it in, as matter from the surrounding denser regions slowly drains into the emptiness. A void powerful enough to cause the flow would likely have diminished in influence over time, meaning the flow should have weakened. The fact that it hasn't suggests the cause is not an absence of matter, but the persistent, unwavering presence of something truly monumental. This points overwhelmingly toward a cause that is both immutable and external. The steady direction and magnitude of the dark flow over cosmic time strongly support the idea of a gravitational source anchored outside our observable universe. Within our expanding cosmos, structures move and evolve, but the source of this pull appears fixed, like a distant lighthouse whose beam has been shining in the same direction since the dawn of time. This fixed external anchor could be an immense, unchanging structure in the greater universe beyond our horizon, or perhaps even the gravitational landscape of the multiverse itself, providing a constant, eternal slope down which our entire visible cosmos has been sliding since its very beginning. When our fundamental understanding of reality is challenged by an observation that refuses to fit, science has two primary paths forward. We can search for something new in the universe, or we can reconsider the laws of physics themselves. Dark flow has proven to be such a powerful anomaly that it has energized a small but dedicated group of physicists to venture down that second, more radical path. They are asking a question that would have been heresy not long ago. What if Einstein's theory of general relativity, the magnificent framework that has guided our understanding of gravity for a century, is not the complete story on the very largest scales? What if dark flow isn't caused by some unseen attractor, but is instead a signature that gravity itself works differently over billions of light years than it does in our solar system? This line of inquiry falls under the umbrella of modified Newtonian dynamics, or MUND, and its relativistic extensions. The original MUND theory was proposed in the 1980s by physicist Mordechai Milgrom as an alternative explanation for the missing mass problem in galaxies, the same problem that led to the invention of dark matter. Milgrom suggested that instead of invoking vast halos of invisible matter to explain why stars at the edges of galaxies orbit too quickly, perhaps Newton's law of gravity experiences a subtle change when accelerations become incredibly tiny, as they do in the deep outskirts of galaxies. In this regime, gravity would become slightly stronger than expected, eliminating the need for dark matter to provide the extra gravitational glue. While MUND had success explaining individual galaxies, it struggled with the larger-scale evidence for dark matter, like the dynamics of galaxy clusters. However, the discovery of dark flow has given a new lease on life to these modified gravity ideas, but on a far grander canvas. Proponents of this view suggest that the coherent motion we see could be a manifestation of a gravitational field that does not weaken with distance in the exact way general relativity predicts. In our standard model, the gravitational influence of any structure, no matter how massive, should become imperceptibly weak across billions of light years. If gravity's range were somehow longer, or if it could be enhanced by the presence of the cosmic microwave background or the overall expansion of the universe, it could potentially create large-scale flows without needing a hidden source of mass. This approach is incredibly appealing to some because it attempts to solve two cosmic mysteries with one elegant revision. It suggests that both the effects we attribute to dark matter and the puzzling phenomenon of dark flow might be two different symptoms of the same underlying cause, a slight but crucial modification to the law of gravity on the largest and most diffuse scales. Instead of filling the universe with invisible matter and then searching for an even more invisible attractor beyond the horizon, this theory proposes a simpler, more economical solution by tweaking the one force we thought we knew so well. Yet, this path is fraught with immense difficulty and faces significant skepticism from the mainstream physics community. General relativity has passed every single test thrown at it with flying colors for a century, from predicting the bending of starlight by the sun to explaining the precise timing of signals from pulsars. Modifying it is not a task to be taken lightly. Any successful alternative theory would not only have to explain dark flow and galactic rotation curves, but it would also have to perfectly reproduce all the stunning successes of general relativity in every other scenario. It's a towering challenge, like asking a new contestant to beat the reigning champion at every single game ever invented. Furthermore, many cosmologists argue that the evidence for the existence of dark matter as a particle is now too compelling to ignore completely. The way massive galaxy clusters bend light from background galaxies, an effect called gravitational lensing, provides a precise map of their total mass, and it consistently shows that visible matter accounts for only a small fraction. A modified gravity theory must also explain this lensing data, and while some relativistic theories can mimic the effects of dark matter in certain situations, creating a complete and consistent framework that explains everything from star orbits to dark flow has so far remained an elusive goal. This ongoing tension between inventing new physics and discovering new matter is a healthy and vital debate, showing that a mystery as deep as dark flow doesn't just provide answers, it fundamentally challenges us to reevaluate how we ask our questions about the nature of the cosmos. As we navigate the labyrinth of possible explanations for dark flow, we must turn our attention to one of the most fundamental and pervasive forces in the cosmos: magnetism. Could the immense magnetic fields that are known to weave through the vast spaces between galaxies be strong enough to orchestrate the motion of entire clusters? This idea proposes that we might not need to look beyond the horizon for a gravitational solution, but instead consider a powerful and ancient electromagnetic force already at work within our universe. The concept rests on the behavior of ionized gas, also known as plasma. The enormous clouds of superheated gas that fill the voids between galaxies within a cluster are not neutral, they are searing oceans of charged particles. According to the laws of electromagnetism, a moving charged particle is deflected by a magnetic field. If a sufficiently powerful and coherent magnetic field were to exist on a truly cosmic scale, stretching across billions of light years, it could theoretically exert a force on this ionized gas. Since this gas makes up a significant portion of a cluster's visible mass, its motion could, in turn, drag the entire cluster along through a process called magnetohydrodynamic dragging. In this scenario, the dark flow would be less a gravitational river and more like iron filings being pulled across a table by a powerful magnet. The appeal of this magnetic model is its grounding in known physics. We have direct evidence that magnetic fields do exist in the intergalactic medium, though they are typically measured to be incredibly faint. A primordial magnetic field, one generated in the universe's first moments and then stretched to unimaginable scales by inflation, could provide a universal framework that influences large-scale motions without requiring any unseen mass. It's an elegant idea that keeps the cause of the flow within the realm of the observable and the known. However, the vast majority of cosmologists and astrophysicists consider this a highly unlikely, almost untenable explanation for the observed dark flow. The primary obstacle is one of sheer magnitude. The force required to move a galaxy cluster is astronomically, almost inconceivably, large. To accelerate thousands of these colossal structures to millions of miles per hour would demand a magnetic field of ridiculous strength, orders of magnitude more powerful than any magnetic field ever detected anywhere in the universe. The energy density stored in such a field would be so immense that it would have left an unmistakable and dramatic imprint on a multitude of other cosmic phenomena, from the propagation of cosmic rays to the pattern of the cosmic microwave background radiation. We see no evidence for such an overwhelming magnetic presence. Furthermore, the magnetic field explanation faces a critical problem with directionality. Magnetic fields exert a force perpendicular to the direction of motion of a charged particle. This creates a spiraling, curved path, not the straight, coherent, and linear flow we observe across thousands of clusters. To create the specific, directional drift of the dark flow, such a magnetic field would need to be perfectly and uniformly aligned across the entire observable universe, which introduces a preferred direction that is just as problematic for the cosmological principle as the flow itself. While the idea of cosmic magnetism is fascinating and plays a crucial role in many other astrophysical processes, it simply lacks the raw power and the specific directional control needed to be the prime mover behind one of the universe's most profound mysteries. So where do we go from here? How do we move past the debate and finally determine if dark flow is a real cosmic current or a magnificent illusion in our data? The answer lies in the next generation of astronomical tools, instruments so precise and powerful they will allow us to map the universe's motions with a clarity we can only dream of today. The path to resolving this mystery is already being paved by ambitious new missions and technologies designed to probe the fabric of the cosmos like never before. At the forefront of this effort are new and more sensitive experiments focused on the cosmic microwave background. While Planck was a monumental leap forward, it is not the final word. Proposed future satellites like the Beyond Planck mission or a potential CMB-S4 ground-based observatory aim to measure the CMB's polarization and temperature with exponentially greater precision. These observatories will be able to filter out the foreground noise from our own galaxy and other astrophysical sources with unprecedented accuracy, essentially giving us a cleaner, sharper hearing aid to listen for the subtle whisper of the kinetic Sunyaev-Zel'dovich effect. With this enhanced sensitivity, they could either confirm the bulk flow with undeniable statistical certainty or reveal it to be a complex artifact, finally settling the core debate that has persisted since 2008. Alongside these dedicated CMB missions, massive new galaxy surveys are set to revolutionize our understanding of large-scale structure. Projects like the European Space Agency's Euclid Space Telescope, NAS and Nancy Grace Roman Space Telescope, and the ground-based Vera-C Rubin Observatory are designed to map the positions and movements of billions of galaxies across an enormous volume of the universe and back through billions of years of cosmic time. By creating a three-dimensional dynamic map of the cosmos, these surveys will allow us to trace the flow of matter directly. We will be able to see not just if galaxy clusters are moving, but precisely how that motion evolves with distance and time, testing whether the flow remains coherent all the way to the edge of the observable universe or if it dissipates, pointing to a cause within our horizon. Perhaps the most futuristic and exciting possibility comes from the emerging field of gravitational wave astronomy. The Laser Interferometer Space Antenna, or LISA, is a planned space-based observatory that will detect low-frequency gravitational waves ripples in space-time caused by the mergers of supermassive black holes. These waves carry information about their source across billions of light-years without being scattered or absorbed. A consistent, preferred direction in the polarization of these waves coming from different parts of the sky could, in theory, provide independent evidence for a large-scale asymmetry in the universe, a subtle warp in spacetime that aligns perfectly with the direction of the dark flow. It would be a completely new line of evidence, one that doesn't rely on light or galaxy clusters at all, but on the very vibrations of the cosmic fabric itself. The convergence of data from these different cutting-edge technologies will be the key to unlocking the mystery. It won't be one single instrument that provides the answer, but the combined power of all of them, each cross-checking and validating the findings of the others. We are on the cusp of a new era of precision cosmology, where the faintest signals and the largest motions will be laid bare. Within the next decade or two, the question of dark flow will likely be resolved, not by argument, but by exquisite data, guiding us either toward a startling new picture of a universe connected to realms beyond, or confirming that the cosmos we see is, after all, the complete and ultimate reality. This statistical tug-of-war lies at the very heart of the dark flow controversy, revealing how the same cosmic data can tell two very different stories depending on how you choose to listen. It's a classic scientific dilemma where the line between a profound discovery and a sophisticated mirage becomes incredibly thin. The core of the debate isn't about the raw data from satellites like WMAP or Planck. It's about the complex statistical processing required to extract a signal that is buried under mountains of cosmic noise. Detecting dark flow is not like hearing a shout in a quiet room. It's like trying to identify a single, specific whisper in the middle of a roaring hurricane. Different research groups make different assumptions about how to filter out that hurricane, and those choices lead them to dramatically different conclusions. One major point of contention revolves around the treatment of foreground emissions. Our view of the pristine cosmic microwave background is obscured by light from our own galaxy, the glow of interstellar dust, the emission from electrons spiraling in magnetic fields, and the radiation from countless stars. To hear the universe's whisper, you must first remove this local cacophony. The team that discovered dark flow, led by Alexander Kashlinsky, employs a specific set of filters and masks to subtract these foregrounds. Their critics argue that their chosen method might be too aggressive or not quite perfect, and that residual contamination from our own galaxy could be mimicking the subtle pattern of a bulk flow. They suggest that what looks like a river of galaxies moving through space might actually be an echo of the Milky Way's own structure, a phantom signal created by an incomplete cleaning of the data. It's the astronomical equivalent of thinking you see a face in the patterns of a stained glass window. The pattern is real, but its meaning is entirely in the eye of the beholder. The other colossal challenge is the sheer number of comparisons being made. When you analyze data from thousands of galaxy clusters across the entire sky, you are performing millions of statistical tests. In any large dataset, random fluctuations are inevitable. If you look hard enough and long enough, you will eventually find patterns that appear significant purely by chance. This is known as the look elsewhere effect. Critics of dark flow argue that the original findings might be a spectacular example of this. They propose that the apparent coherence in the motion of the clusters could be a random alignment, a cosmic coincidence that stands out simply because we have the statistical power to find it. To test this, other research groups have performed meticulous, null tests. They run the same analysis on simulated data that is known to have no bulk flow, using computer-generated universes that obey the standard cosmological model. In some of these tests, patterns that look eerily similar to dark flow occasionally appear, suggesting that such a signal can indeed arise from random noise. This doesn't prove dark flow is false, but it does show that its statistical significance is far from a settled matter. This has led to a situation where different teams, all comprised of brilliant and respected cosmologists, can look at the same dataset from the Planck satellite and publish papers that directly contradict each other. One group's rigorous analysis concludes with 99.7% confidence that a large-scale flow exists. Another group's equally rigorous analysis, using a different statistical pipeline and a different catalog of galaxy clusters, finds the signal vanishes entirely, dropping to a level of confidence that is statistically meaningless. This isn't a sign of failure or incompetence. It is a fascinating and honest reflection of how cutting-edge science operates at the very limits of detectability. The debate over dark flow is a masterclass in scientific skepticism, demonstrating that a result isn't truly robust until it can survive the scrutiny of multiple independent methods and emerge consistently. For now, dark flow remains in a tantalizing limbo, a compelling possibility that has yet to achieve the universal consensus required to rewrite our textbooks, ensuring it remains one of the most provocative and hotly debated topics in modern cosmology. This immense current we call dark flow doesn't exist in a vacuum. It's part of a grand, nested hierarchy of motion that defines our dynamic place in the cosmos. To truly appreciate its scale, we need to pull back from the edge of the observable universe and start much closer to home, with the gravitational dances we can see and measure directly. Our own Milky Way galaxy is not a stationary island in space. It's in a constant, graceful motion, pulled by the gravitational tides of its most massive neighbors. The entire local group of galaxies, which includes Andromeda and dozens of smaller satellites, is itself drifting toward the heart of our local supercluster. This movement is a gentle but persistent flow toward the immense gravitational anchor known as the Virgo cluster, a sprawling metropolis of over 1,000 galaxies about 54 million light-years away. This is our most immediate and well-understood cosmic current, a local river within a much larger watershed. But the story doesn't end in Virgo. This entire complex, including our local group and the Virgo cluster itself, is part of an even vaster structure known as the Laniakea supercluster. Laniakea, which means immeasurable heaven in Hawaiian, is a breathtaking web of galaxies spanning over 500 million light-years. All the matter within Laniakea is flowing toward a single, powerful gravitational focal point, a region astronomers call the Great Attractor. For decades, this mysterious concentration of mass, hidden behind the dusty plane of our own galaxy, was a major cosmic puzzle in its own right. We now understand it to be the core gravitational heart of our supercluster, the point toward which every galaxy in our extended neighborhood is slowly, inevitably drawn. This is the next level up in the hierarchy, a continental scale flow that governs the motion of millions of galaxies. Now, here is where dark flow redefines the entire picture. The Great Attractor, for all its immense power, is a phenomenon within our observable universe. Its influence, while colossal, is ultimately local on the grandest cosmic scales. Dark flow is something entirely different. The galaxy clusters caught in this mysterious current are not simply moving toward a known point like the Great Attractor. Their motion is additive. They are participating in the local flows toward Virgo, toward the Great Attractor, within Laniakea, while also being carried by this additional, far more powerful and coherent drift. Imagine a leaf floating down a small stream that feeds into a river, which itself flows into a mighty ocean current. The leaf is moved by all these forces at once. Dark flow is that final, overwhelming ocean current, a directional pull so immense that it operates on a scale that encompasses not just our supercluster but thousands of them. It suggests that even the majestic gravitational pull of the Great Attractor, the force that guides our entire local universe, is itself just a minor tributary in a cosmic river system of unimaginable proportions, all flowing toward a destination we cannot see. For over half a century, our theories of galaxy formation have rested on a beautifully simple, bottom-up principle. It's a cosmic story of humble beginnings, where tiny quantum fluctuations in the infant universe were amplified by gravity's relentless pull. These slight overdensities acted as seeds, gradually attracting more and more dark matter and gas. Over billions of years, these seeds grew into the first stars, then galaxies, which then merged and clustered together into the vast web of filaments and voids we see today. In this standard model, the largest structures, the superclusters, are simply the final, most enormous nodes in this cosmic network. Their formation is dictated primarily by the local gravitational landscape, the pull of their immediate neighbors, and the surrounding dark matter. The idea that something on a scale 10 times larger than a supercluster could directly influence this process was, until recently, almost unthinkable. Dark flow shatters that comfortable narrative, introducing the possibility of a top-down influence so profound it would rewrite the first chapters of every cosmology textbook. This isn't just about adding a new paragraph, it's about reworking the entire plot. If dark flow is real, it means that from the very moment of their birth, the seeds that would become galaxies were not distributed randomly. They were planted on a cosmic landscape that already had a profound and fundamental tilt, a pre-existing slope in the fabric of spacetime established by gravitational influences from beyond our horizon. Imagine trying to grow a forest, but the entire continent is already tilting toward the east. Every single tree, every single plant will grow in a way that is subtly influenced by that overall gradient. Its roots will spread differently, its trunk will lean slightly. In the same way, the formation of every galaxy and cluster within our observable universe may have been gently but persistently nudged by this immense external gravitational field. The initial conditions for structure formation were not isotropic, they had a preferred direction baked in from the very beginning. The implications for the evolution of galaxies are staggering. A key puzzle in modern astrophysics is why galaxies in different large-scale environments, like dense clusters versus sparse voids, can have such different properties from their shapes and sizes to their rates of star formation. We've always attributed these differences to local conditions. A galaxy in a crowded cluster interacts with its neighbors, has its gas stripped away, and evolves differently than an isolated galaxy in a quiet void. But dark flow suggests that their very destinies may have been partially set at birth by this large-scale flow. The trajectory of a protogalactic cloud of gas billions of years ago wouldn't just be determined by the pull of the dark matter halo it was collapsing into, but also by this overarching current. This could explain perplexing large-scale alignments of galaxy spins or peculiar large-scale patterns in galactic properties that have no comfortable explanation in the standard bottom-up model. The greatest revolution would be in our understanding of the cosmic web itself. This vast, intricate network of filaments and nodes is not static. It is a dynamic highway along which galaxies travel, funneled by gravity toward the largest clusters. Dark flow proposes that this entire highway system, on the very largest scales, is not merely a product of local gravity, but is itself aligned and oriented by an external force. The filaments might not just be connecting clusters within our observable universe, they could be tributaries feeding into a cosmic river system that extends into the unknown. The largest structures we know, the superclusters, would no longer be the end of the line. They would become waypoints, grand central stations in a journey that continues toward a destination we cannot see. This would transform our view of the cosmos from a self-contained entity into what might be just one province in a far grander and more complex empire, whose true capital lies forever in the darkness, its gravitational influence the only evidence of its majestic and overwhelming presence. Given that dark matter constitutes the overwhelming majority of the universe's mass and provides the gravitational scaffolding for all cosmic structures, it's only natural to wonder if this invisible substance could be the key to unlocking the dark flow mystery. After all, the gravitational tug we're detecting must come from somewhere, and the sheer amount of mass required points directly to the domain where dark matter reigns supreme. The halos of dark matter that envelop galaxies and thread through the cosmic web are the true architects of large-scale motion, guiding the dance of visible matter through their immense but unseen gravitational influence. If we are to find an explanation within our known universe, it almost certainly must involve the distribution and behavior of dark matter on scales we are only beginning to map. To grasp how dark matter might be involved, we need to consider its role not just locally but universally. The standard cosmological model, known as lambda cold dark matter, pictures a cosmos where dark matter is smoothly distributed on the largest scales, with only minor fluctuations that grew over time into the galaxies and clusters we see today. In this model, the gravitational pull from all the dark matter within our observable universe should, on average, cancel itself out on these enormous scales, resulting in the random, chaotic motions that the cosmological principle predicts. The existence of dark flow directly challenges this picture, suggesting that the dark matter distribution is not smooth and uniform after all, but may contain imbalances or gradients of incredible magnitude. One compelling possibility is that we have simply underestimated the size and power of dark matter structures within our own observable cosmos. Could there be a concentration of dark matter so vast, so immense, that its gravitational pull extends across billions of light years, orchestrating the motion of thousands of galaxy clusters? Imagine a cosmic continent of dark matter, a structure an order of magnitude larger than the largest known supercluster, whose gravitational shadow is only now being felt through its effect on everything within our horizon. This wouldn't require new physics or realms beyond our view, merely a recognition that the cosmic web of dark matter might be woven with threads far thicker and longer than our current maps suggest. The Great Attractor was once such a hidden overdensity, now understood to be part of the larger Laniakea supercluster. Perhaps dark flow is pointing us toward the next tier in this hierarchy, a structure of almost mythical proportions we have yet to directly detect. However, this appealing idea runs into a formidable problem of scale and timing. For a dark matter structure within our observable universe to cause the observed flow, it would need to contain far more mass than is believed to exist in our entire visible cosmos. Our most precise measurements of the total matter density from the cosmic microwave background and large-scale galaxy surveys give us a very reliable estimate of how much stuff is out there. There simply doesn't appear to be enough dark matter within our 46 billion light-year wide horizon to form a lump massive enough to generate such a powerful and coherent gravitational gradient. The required structure would be so colossal that it would itself constitute a catastrophic violation of the cosmological principle, making the universe fundamentally lumpy and anisotropic on its very largest scales. In trying to solve one mystery with dark matter, we might inadvertently create another, equally profound one. This has led some theorists to propose more exotic versions of dark matter itself. What if dark matter isn't entirely cold and passive? Certain models suggest a fraction of dark matter could be self-interacting or even possess a small electric charge, allowing it to clump in ways that ordinary cold dark matter cannot. Other, more speculative ideas involve dark forces that operate only between dark matter particles, creating long-range interactions that could, in theory, amplify its gravitational influence across vast distances. While these ideas are fascinating, they remain highly speculative, lacking any direct experimental evidence. They essentially exchange one mystery for another, replacing the puzzle of dark flow with the puzzle of a new type of dark matter for which we have no other compelling need. The most significant challenge for any dark matter-based explanation remains the precise coherence and direction of the flow. The motion isn't a general drift, it's a remarkably uniform current across a volume of space that encompasses thousands of galaxy clusters. A single, even unimaginably large, knot of dark matter would likely create a more focused, cone-like pattern of attraction, with clusters closer to the source moving faster and on a more direct path than those farther away. The data we have suggests something different, a more uniform motion that hints at a constant gravitational slope across the entire observable universe. This is less like being pulled by a single magnet and more like the entire room is tilted. This subtle distinction points away from a local dark matter over density and toward an influence that is both external and universal, a fundamental asymmetry written into the very fabric of the cosmos that has guided the distribution of dark matter from the very beginning. While dark matter is the medium through which the force of dark flow is transmitted, it may not be its ultimate source, leaving us to look even further for the origin of this cosmic current. Beyond the equations and the data, dark flow forces us to confront questions that have haunted philosophers for millennia, challenging the very framework through which we perceive reality. If this mysterious current is real, it suggests that our entire observable universe, with its hundreds of billions of galaxies, might not be a self-contained whole but merely a small province within a far grander structure whose true nature is forever hidden from our view. This isn't just a scientific adjustment, it's a philosophical earthquake that reverberates through our understanding of existence, knowledge, and our place within the cosmos. It resurrects the ancient concept of the cosmological horizon, but not as a simple limit of our technology. It becomes a fundamental boundary of knowledge, a veil beyond which we may forever be unable to see, yet whose influence we can tangibly feel. We are like sailors on an ocean, deducing the existence of a distant continent solely by the consistent direction of the currents and the unfamiliar birds that occasionally drift overhead, forever wondering about the shape of the land we can never visit. This introduces a deeply humbling and potentially unsettling limitation on human comprehension. For centuries, the project of science has been built on the optimistic principle that through observation and reason, we can ultimately understand the universe in its entirety. Dark flow whispers a cautionary tale that there might be fundamental aspects of reality that are, by their very nature, inaccessible to us. The cause of this flow could be something profoundly alien, a structure governed by different physical laws, a different geometry of space-time, or a different balance of fundamental forces that we cannot even conceive of from within our own cosmic bubble. Our entire physics is built from observations made inside this bubble. How can we ever develop the tools or the language to describe what exists outside of it? We are effectively trying to solve a jigsaw puzzle where the most important pieces are not just missing, but are locked in a box to which we have no key, forever leaving our picture of reality incomplete. Yet there is a profound beauty in this limitation. Dark flow doesn't just highlight what we cannot know, it also illuminates a new path to knowledge itself. It teaches us that we can learn about the unseen not only through direct observation but also through its subtle gravitational echoes. We are inferring the existence of a cosmic landscape from the gentle tilt of our own. This expands the very definition of scientific inquiry, moving it from a purely empirical endeavor to one that must also embrace powerful inference and the careful study of indirect effects. It transforms cosmology from a practice of simply mapping what we see into a discipline of cosmic detective work, where the clues are imprinted in the motion of galaxies and the ancient light of the Big Bang. In doing so, dark flow doesn't signal the end of understanding but the beginning of a more nuanced and sophisticated kind of understanding, one that accepts the unknown not as a failure, but as an integral part of the majestic and mysterious whole. To truly appreciate the strangeness of dark flow, we need to place it beside the most fundamental and predictable motion in the entire cosmos, the Hubble flow. This is the grand, relentless expansion of the universe itself, first observed by Edwin Hubble nearly a century ago. He discovered that galaxies are all moving away from us, and crucially, the farther away a galaxy is, the faster it appears to be receding. This isn't because galaxies are speeding through space like projectiles. It's because the very fabric of space-time between them is stretching. Imagine drawing dots on a deflated balloon and then blowing it up. The dots themselves aren't moving across the surface of the balloon, but the space between them expands, causing each dot to see all the others moving away. The Hubble flow is this balloon expansion on a cosmic scale, a smooth, uniform, and omnipresent drift that affects every single galaxy equally, carrying them apart on the rising tide of expanding space. This expansion is the default setting of the universe, the backdrop against which all other motions are measured. Cosmologists call any movement that deviates from this uniform expansion a peculiar velocity. These are the local, irregular motions caused by the gravitational tug of war between nearby objects. Our Milky Way, for instance, has a peculiar velocity as it's pulled toward the Andromeda Galaxy and toward the center of the Virgo cluster. These motions are like small ripples on the surface of a vast, rising ocean. They are expected, manageable, and explained by the gravitational influence of visible structures within the cosmos. The key point is that these peculiar velocities are local. Over sufficiently large distances, the sheer power of the Hubble expansion should dominate, and any random gravitational pulls should cancel each other out, leaving behind only the smooth, predictable drift of the universe's growth. Dark flow shatters this expectation completely. It is not a local ripple, it is a peculiar velocity on a monstrous, cosmological scale. What we are witnessing is not just a deviation from the Hubble flow, but a coordinated deviation. Thousands of galaxy clusters, separated by billions of light years, are all moving in the same specific direction relative to the expansion. This is akin to watching that expanding balloon and seeing every single dot, no matter where it is on the surface, also sliding steadily toward one particular edge. The Hubble flow is carrying everything apart, but dark flow is acting like a mysterious slope on the surface of the balloon, causing everything to also slide sideways in unison. This is why the distinction is so crucial for cosmology. The Hubble flow is the predictable, smooth expansion driven by dark energy, while dark flow is an anomalous, directional motion that must be caused by something else entirely. A gravitational influence so vast it overrides the local chaos and imposes order on an unimaginable scale, suggesting our universe is not the isotropic expanse thought it was. To test the limits of our understanding, cosmologists have turned to some of the most powerful tools in modern science: immense supercomputer simulations that can create entire virtual universes from the ground up. These aren't simple video games, they are incredibly complex mathematical models that codify all our known laws of physics and cosmology. Scientists can set the initial conditions, the recipe of dark matter, dark energy, and the primordial fluctuations from the Big Bang, and then press play, watching billions of years of cosmic evolution unfold in a matter of days or weeks. The goal is to see if a universe that obeys all our standard rules can spontaneously produce something as bizarre and coherent as the dark flow we seem to observe in our own. Running these simulations is a monumental task requiring vast computational resources. They track the gravitational interactions between trillions of particles of dark matter, modeling how they clump together to form halos that will eventually host galaxies and clusters. The most advanced simulations, with names like Illustris TNG and Millennium, can create cosmic volumes billions of light years across, containing millions of virtual galaxies. Researchers then analyze these digital universes in exactly the same way they study the real one, by calculating the predicted motions of their simulated galaxy clusters and looking for any sign of a large-scale bulk flow. It's the ultimate test. If our standard model is correct, these virtual cosmos should look and behave just like our own. The results from these digital laboratories have been both clarifying and deeply challenging. When simulations are run using the standard lambda-cold dark matter model, with a universe that is homogeneous and isotropic on the largest scales, they consistently fail to produce anything resembling the scale and coherence of dark flow. The peculiar velocities of galaxy clusters in these virtual worlds are exactly what theorists predicted. They are random, local, and relatively small. Any large-scale motions that do emerge are weak and disorganized, cancelling each other out across the vastness of the simulation. The virtual clusters drift with the Hubble flow, their motions dictated solely by the gravitational pull of structures within their own observable universe. There is no mysterious, coordinated river of matter flowing toward a single point on the horizon. According to these simulations, dark flow simply should not exist in a universe that follows all the established rules. This persistent failure is in its own way a significant result. It strongly suggests that dark flow cannot be explained by any known structure or distribution of matter within our cosmic horizon. The simulations are telling us that the combined gravitational pull of every galaxy, every filament of dark matter, and every supercluster we know of is utterly insufficient to create the observed effect. This forces cosmologists to consider more radical possibilities. Perhaps the initial conditions programmed into the simulations are incomplete. Maybe the primordial universe wasn't as smooth as we've assumed and was imprinted with a fundamental asymmetry from the very beginning. Some researchers have begun running modified simulations that introduce such a tilt, a pre-existing gravitational gradient across the entire virtual cosmos. In these altered worlds, a large-scale flow does emerge, acting as a constant current that guides the formation of structures from their earliest moments. Other simulations explore even more exotic ideas, like the gravitational influence of other universes in a multiverse. While this is far more speculative, the principle is to see if such an external pull could leave a detectable imprint on the evolution of a universe like our own. These digital experiments are pushing the boundaries of computation and theory alike, serving as a crucial bridge between raw observation and profound explanation. They haven't yet provided a definitive answer, but they have brilliantly framed the question. By demonstrating that our standard model cannot account for dark flow, these supercomputer universes have elevated the phenomenon from a curious anomaly to a potential key, a key that might unlock a deeper understanding of reality, forcing us to rewrite the initial conditions of the cosmos or perhaps even peer beyond its edge. Attempting to pinpoint the location of dark flow's source is a task that stretches the very limits of cosmology and forces us to confront the true scale of the unknown. To generate a coherent gravitational pull powerful enough to move thousands of galaxy clusters in near-perfect unison, the source of this immense force cannot be close by. It must be almost unimaginably distant. The very coherence of the flow is the key clue here. If the source were relatively nearby within our observable universe, its gravitational influence would create a converging pattern, like rivers flowing into a single lake. Clusters closer to the source would be pulled more directly and with greater force than those farther away, creating a fan-like effect in their motions. But that's not what we see. Instead, we observe a remarkably uniform motion across a vast volume of space, which suggests the source is so profoundly far away that its gravitational pull appears almost as a constant, uniform slope across our entire observable horizon. It's the difference between standing near a single powerful magnet and feeling its specific pull, versus finding yourself on a planet with a perfectly level magnetic field that pulls everything in one direction. The latter implies a source whose scale and distance are beyond our everyday comprehension. Scientists have turned to complex gravitational models and simulations to put numbers to this staggering distance. Some of the most compelling calculations estimate that the source of this pull must lie at a minimum of several hundred billion light-years away from us. To grasp the sheer immensity of that number, remember that our entire observable universe, everything we could possibly see with any telescope, spans a mere 93 billion light-years in diameter. The suspected source of dark flow, therefore, lies multiple times farther away than the absolute edge of everything we can observe. This means the structure doing the pulling is not just outside our field of view. It is so far beyond our cosmic horizon that its light will never, even in principle, be able to reach us, no matter how long we wait or how advanced our technology becomes. We are forever separated from it by an insurmountable gulf of expanding space-time. This estimation isn't just a wild guess, it's derived from the strength and uniformity of the flow itself. The gravitational force an object exerts weakens with the square of the distance from it. To exert a force strong enough to be detectable across tens of billions of light years, yet uniform enough to not tear structures apart, requires an object of almost inconceivable mass positioned at a very specific range. If it were too close, its pull would be catastrophic and uneven. If it were too far, its influence would be too weak to detect. The fact that we see this effect at all points to a sweet spot in distance, a location so far that its pull is nearly uniform across our entire visible cosmos, yet anchored by an object so monstrously massive that its gravity remains potent across those mind-numbing distances. This suggests we are not just sensing a neighboring supercluster, but the gravitational shadow of a cosmic structure so vast it could make our entire observable universe seem like a mere suburb in comparison, a testament to the fact that the full universe, the grand totality of all that exists, is likely orders of magnitude larger and more magnificent than the tiny portion we are privileged to call home. Given its dramatic name and its association with other cosmic mysteries, it's no surprise that dark flow has generated its fair share of public confusion. One of the most common misunderstandings is simply mixing it up with its more famous cousins, dark matter and dark energy. It's an easy mistake to make. They all share that evocative word, dark, hinting at something unseen and unknown. But as we've explored, they represent three entirely different puzzles. Think of it this way: dark matter is the invisible scaffolding that holds galaxies together. Dark energy is the mysterious force pushing the entire universe apart, and dark flow is the unexplained river of motion, a directional current that seems to flow through that expanding universe. One builds structures, one expands space, and one moves structures in a coordinated way. They are three distinct chapters in the same grand cosmic mystery novel, not different names for the same thing. Another frequent misconception is the idea that dark flow means everything in the universe is moving toward a single, specific point, like water spiraling down a drain. This paints a terrifyingly claustrophobic picture of a cosmos destined to collapse into a single, unimaginable crunch, but that's not what the data shows at all. Remember the Hubble flow. The universe is still expanding and galaxies are still moving apart from each other. Dark flow is a different kind of motion superimposed on top of that expansion. It's not a collapse, it's a drift. A helpful analogy is to imagine a vast, inflating balloon again. As the balloon expands, all the dots on its surface move apart. Now imagine that the entire surface of that balloon is also tilted. The dots are still moving apart due to the inflation, but they are also all sliding sideways down the gentle slope. They aren't all converging on a single point. They are all moving in the same direction while the space between them continues to grow. This is the nuanced reality of dark flow, a persistent directional preference within an ever-expanding cosmos. Some people also hear about this and assume we've found a center to the universe or a preferred up and down, which would completely upend the cosmological principle. It's crucial to understand that from our perspective here on Earth, the flow appears to be pointing toward a specific patch of sky, but that's just our particular viewpoint. An observer in a galaxy cluster millions of light years away would also see clusters on their horizon drifting in a specific direction which might be different from ours. The phenomenon isn't about everything moving toward one absolute point in space. It's about large-scale coherence. It suggests that if you could stand in any one of those thousands of flowing clusters, you would observe your neighbors moving in a synchronized way relative to the overall expansion. This doesn't establish a center. Instead, it introduces a large-scale directionality, a subtle grain to the cosmos like the weave in a piece of fabric, which is a profound departure from the idea of perfect smoothness in all directions. Finally, there's a popular but incorrect notion that dark flow is a settled scientific fact, a confirmed discovery that has already rewritten the textbooks. In reality, as we've seen, it remains one of the most hotly debated topics in modern cosmology. The conversation between the researchers who defend the signal and those who attribute it to statistical noise or systematic error is a perfect example of the scientific process working as it should, with rigorous skepticism and demands for extraordinary evidence. Presenting dark flow as an undeniable truth does a disservice to the fascinating and ongoing detective work. It's not a closed case, it's an active investigation, a compelling hint that drives us to build better telescopes and devise more clever tests. The true story of dark flow isn't just about a mysterious current. It's about how scientists grapple with the unknown at the very edge of understanding. A reminder that the most exciting discoveries are often those that remain just out of reach, compelling us to keep looking. To venture into the origins of dark flow is to journey back to the very beginning of everything, to a time when the universe was a seething, energy-dense froth smaller than a single atom. In this unimaginable environment, the dominant force was not gravity, but quantum mechanics, the strange and probabilistic rules that govern the behavior of particles on the smallest scales. According to our best theories, the vacuum of space at this time was not truly empty. It was a turbulent sea of quantum fluctuations where pairs of particles and antiparticles would spontaneously blink into and out of existence, borrowing energy from nothing for the briefest of moments. It is from this chaotic, foamy foundation that our entire cosmos is thought to have arisen, and the seeds for all future structure, including perhaps the mysterious dark flow, may have been planted in these first fleeting instants. The leading theory of cosmic inflation proposes that this quantum froth was stretched to astronomical proportions in the tiniest fraction of a second after the Big Bang. A microscopic fluctuation, a random denser patch in the quantum foam, could have been inflated to a scale of billions of light years, becoming the gravitational seed for a future supercluster. This process is how we explain the slight variations in the cosmic microwave background. Those tiny temperature differences are the amplified fingerprints of quantum noise. But what if the process wasn't perfectly uniform? What if, by pure chance, the quantum fluctuations that were stretched across our entire observable universe were not completely random, but contained a tiny, fundamental imbalance? Imagine shaking a bag of confetti and then stretching the entire bag to the size of a continent. Most of the confetti would be spread evenly, but if your initial shake had a slight bias, perhaps a few more pieces drifted to one side, that small preference would now be magnified into a continent-scale gradient. This is the fascinating speculative link to dark flow, a minuscule preferential direction or asymmetry in those primordial quantum fluctuations could have been imprinted onto the fabric of spacetime during inflation. This wouldn't be a gravitational pull from a massive object, but rather a fundamental tilt or texture woven into the geometry of the universe itself from its birth. Over the next 14 billion years, as matter congealed from energy and collapsed under gravity to form galaxies and clusters, this underlying tilt would have acted as a gentle but persistent guide. Every structure that formed would have felt this subtle slope, this cosmic preference for motion in one direction. The dark flow we observe today in this speculative view would not be a river being pulled by a distant mountain, but the entire landscape of the universe gently sloping toward a specific point on its horizon. It would be the ultimate cosmic fossil, a remnant of a random quantum event from the first moment of time, preserved and magnified to a scale that governs the motion of galaxy clusters. This idea pushes the limits of our understanding, connecting the bizarre, probabilistic world of the quantum to the grand, deterministic motions of general relativity. It suggests that the largest structures we can observe are dancing to a tune composed in the first note of creation, a rhythm set by the random flicker of particles in the void. While this connection remains highly theoretical and incredibly difficult to prove, it offers a profound and elegant possibility that the answer to one of cosmology's greatest modern mysteries might lie hidden in the very first quantum whispers of the universe. What if, after all the debate and scrutiny, we one day receive undeniable confirmation that dark flow is not an error, not a statistical fluke, but a real and profound feature of our cosmos? The implications would be nothing short of revolutionary, sending ripples through the entire field of physics and fundamentally altering our cosmic perspective. It would mean that our entire observable universe, with its hundreds of billions of galaxies, is not the final frontier but merely a local neighborhood, a single drifting island in a much vaster and more mysterious ocean whose shores we cannot see. This confirmation would force us to accept that the grand, seemingly infinite expanse we call home is subject to influences from beyond its borders, that we are part of a structure so immense it defies our current comprehension. The most immediate and staggering consequence would be the existence of structures on a scale we previously thought impossible. To generate the gravitational pull required for dark flow, the source would need to be a concentration of matter of almost inconceivable proportions, a cosmic continent that makes our largest superclusters look like tiny villages. This would shatter the cosmological principle, the foundational idea that the universe is smooth and uniform on the largest scales. Instead, we would have to adopt a new view of a deeply textured and hierarchical cosmos, with alternating realms of immense density and profound emptiness stretching far beyond our horizon. Our maps of the universe would suddenly become woefully incomplete, showing only a small province of a much grander empire whose true capital lies forever in darkness. This discovery would inevitably demand a revolution in physics itself. Einstein's theory of general relativity, which has perfectly explained gravity within our observable cosmos for a century, might need to be modified or extended to account for such a vast external influence. We might be forced to develop a new theory of quantum gravity or embrace more exotic ideas, like the existence of extra dimensions through which gravity can subtly leak. The very laws we consider fundamental might turn out to be local bylaws specific to our own cosmic bubble. Confirming dark flow wouldn't just add a new chapter to our physics textbooks, it would require us to write an entirely new volume, one that describes a reality far more complex and interconnected than we ever imagined. Perhaps the most mind-bending possibility is that dark flow could provide our first tangible evidence for the multiverse. If the pull is coming from a region whose light cannot possibly reach us, even in principle, then one of the few plausible explanations is the gravitational tug of another universe entirely, a separate cosmic bubble with its own physical laws and history, brushing against our own in a higher dimensional reality we cannot perceive. This would transform cosmology from the study of a single universe to the study of a vast multiversal landscape, making our home just one reality in an infinite tapestry of existence. The philosophical implications are profound, suggesting that our universe is not unique or special, but one of countless others, each with its own story. Ultimately, confirming dark flow would be a humbling and awe-inspiring reminder of our place in the cosmos. We are not passive observers of a static stage. We are participants in a dynamic, flowing universe caught in a current that began at the dawn of time and flows toward an unknown destination. It would redefine the goal of science, shifting our mission from mapping the visible to deciphering the invisible, from studying what is present to inferring what must lie beyond. This wouldn't signal an end to discovery, but the beginning of a new and even more exciting journey, one that challenges us to understand not just our universe, but our universe's place within a reality of truly unimaginable scale and grandeur. And so, after this incredible journey through 30 astonishing facts, we are left standing at the edge of the known universe, humbled and awestruck by the profound mystery of dark flow. We've seen how this coordinated river of galaxy clusters, moving at millions of miles per hour, challenges the very core of modern cosmology, suggesting that our entire observable cosmos might be just a small part of a much larger hidden structure. From its discovery in the subtle shifts of the cosmic microwave background to the fierce scientific debates it has sparked, dark flow represents a frontier, a tantalizing clue that there is so much more to existence than what we can directly see with our most powerful telescopes. It whispers of gravitational influences from beyond our horizon, of potential connections to other universes, and of cosmic textures woven into the fabric of space-time at the moment of creation itself. Phenomena like this are what truly push the boundaries of human knowledge. They remind us that science is not a static set of facts in a textbook, but a living, breathing process of discovery, debate, and wonder. It is in these moments, when our most cherished theories are challenged by the stubbornness of data, that we have the greatest opportunity to grow and learn. Dark flow forces us to ask bigger questions, to dream bigger dreams, and to acknowledge that the universe, in all its majesty, is far stranger and more wonderful than we could have ever imagined. It is a beautiful reminder that the cosmos is under no obligation to conform to our expectations, and that the greatest adventures of discovery still lie ahead of us. So, as we conclude this exploration, I want to encourage you to carry this sense of curiosity with you. The next time you look up at the night sky, remember that it is not a static painting, but a dynamic, flowing river of stars and galaxies, full of secrets waiting to be uncovered. The universe is speaking to us through mysteries like dark flow, and it is up to us to listen, to question, and to never stop wondering. What do you think is causing this immense cosmic current? Do you believe it points to a multiverse, or is there another explanation we haven't even conceived of yet? I would love to hear your thoughts, your questions, and your own sense of wonder. Share them in the comments below, and let's continue this conversation about the endless wonders that await us in the great unknown.